Hello students, today we will find the fringe width of interference patterns for minima and maxima, and we will also find the fringe width for the central maxima. Well, you see, in this case of diffraction we have dealt mathematical method we have adopted was so that we can satisfy the formation of fringe at particular point due to diffraction, and since we were having so many points on the wave front which served as the secondary wavelets, and therefore it was very difficult to deal with each individual secondary wavelets reaching the point P on the screen, where we have to find whether the brightness is high or maxima is produced or minima is produced over there. And for that we have made the assumptions that the whole wavefront were divided into two parts or even number of parts whenever we intended to find the condition for dark bands, and whenever we intended to find the condition for bright fringe, we divided the whole wavefront in odd equal number of parts, and then each time we took the path difference for each divided part of the wavefront to be equal to lambda by 2. And for in case of the secondary maxima, we were having odd number of wave path difference which were having opposite phase, means they differed in phase by path by lambda by 2, and therefore the except one, rest all the parts were cancelling each other, and so the only uncancelled part was responsible for producing the bright fringe over there, and therefore the intensity of the maxima also keeps decreasing while its order is increasing. The intensity of second maxima will be quite less than the intensity of first maxima, and so on and so forth. Similarly, we dealt with the secondary minima, and we divided the whole wavefront in even equal parts, and each part was producing a path difference of lambda by 2, and therefore each pair of such parts of the wavefront reaching point P cancel each other, and therefore brightness was nearly zero. Today we are going to find the fringe width, and we have already derived this relation for minima is sin theta, the angular separation, the angle by which the ray is bending from the original path O01, and we found that sin theta is equal to n lambda by a, where n is the order of the secondary fringe. And for minima we also derived this sin theta was equal to 2n plus 1 lambda by 2a, where n is an integer and it refers the number of secondary minima which we are addressing, and accordingly we place the value of n equal to 0, 1, 2, 3, etc. Now from this triangle O01P we have sin theta is nearly equal to tan theta if this angle is taken to be very small, and therefore we can write tan theta equal to perpendicular, that is PO dash, and which is nothing but equal to x we have already discussed it. The distance of that point under consideration from the center of the screen, and divided by OO dash, that is the distance of screen from the slit. So that becomes x by d, and we have named it equation 1, 2 and 3. Now if we want to find the, if we equate these two equations, equation 3 and equation 1, what we have is, you see, sine theta is equal to x upon d and sine theta is equal to n lambda upon a. Therefore we have x by d is equal to n lambda by a. Therefore x and the nth fringe equal to n lambda d by a. And naturally, if we find the distance of next higher order, we have xn plus 1 equal to n plus 1 lambda d by a. Now it is very much obvious that we have the pattern central bright fringe is formed about O1 and followed by first minima and then first maxima and so on and so forth. So that means if we want to find the fringe width of nth maxima, say for example first maxima, that means n equal to 1, for that what we need to do is find the difference between the distance of second minima and the distance of first minima. So distance of second minima means if we have n equal to 1, but here we are taking in general case, so we write distance of n plus 1th minima minus distance of nth minima, and so here you see lambda d by a is common in both of these equations. Therefore we have n plus 1 minus n equal to d lambda by a. This is the fringe width of the minima, which is which is sandwiched by the two. This is the width of maxima, which is sandwiched by two minima. So we can call this equation number 5a. And for central maxima, what we need to do is we find the thickness of central maxima. What you see in central maxima, you have some distance from center up to which the central maxima exists on one side, and this by same distance is exist on the other side. So the total thickness of the central maxima must be equal to the thickness of the distance of the first minima from the center into 2. So we have thickness of central maxima equal to twice the distance of first minima from the center, and that is, we know, lambda d lambda by a. This is the distance of first minima. If we have n equal to 1, we get 1 plus 1, that is 2 lambda by 2a, and that becomes d lambda by a. Distance of here you see d lambda by a, and therefore this is for equation minima, and therefore you see you have n, for n equal to 1 we have lambda d by a. We use equation 4a over here for putting the value of x. We use equation 4a. This is equation 4a. Used equation 4a, and therefore the width of central maxima will be 2 d lambda by a. We call it equation 5b. Now in same pattern we can find the fringe width of minima. What we need to do is, I leave this as an exercise for you. We again do the same work. We have to find the thickness of minima. So what we do is, we find the difference between of the distance of nth maxima and the distance of n plus 1th maxima from the center, and that will give the thickness of the n plus 1th minima, and that is how we have found it. And what we see is that the thickness of minima is equal to thickness of maxima, and it is independent of the number order, first secondary or second secondary or third secondary, maxima or minima, be whatever it be, the thickness of the fringe remains same. One thing what you need to recognize and remember, that the fringe width for minima and maxima is d lambda by a. You see, d lambda by a, and therefore you can very much understand that since thickness is directly proportional to wavelength, therefore greater is the wavelength, greater is the thickness of the fringe, and that means for red light we have the broadest fringe width of maxima or minima, secondary maxima or minima. Now one thing we have also found, that the central maxima is equal to 2 d lambda by a, and therefore you can very much understand that central maxima is, width of central maxima is inversely proportional to the slit width a. So if this slit width is made more wide, then the central maxima will become thinner. If we make the slit width wide, then the central maxima will become narrower, thinner, because they are inversely proportional. And therefore the fringe width of secondary maxima and minima will become very less, not observed, and only the central maximum might be observable, and that means it is producing the image of slit. That's all for today. Thank you. Have a nice day.